Hey, welcome to High School Physics. My name is Rex. In the last chapter, we talked about units and measurement and how they help us in our everyday life. Today, I'm going to talk about motion. And I'm going to divide this video into part 1, which is going to define motion, talk about the types of motion, relative motion, distance, displacement, speed and velocity, and acceleration. And then part 2 is going to talk about types of forces and friction, and also angular velocity and acceleration. Now, let's dive into this one. The definition and types of motion. What is motion? Motion is the movement from point A to point B. Duh, that's obvious. But what are the types of motion? Because there are obviously ways you can get from point A to point B. So there are 4 basic types of motion. Number 1, there is translational motion. Translational motion. What is translational motion? Translational motion is the movement from point A to point B, either in a straight line or in a curved path. The movement from point A to point B that is translational, that's in a straight line, is called rectilinear motion. But the movement in a curved path is just translational motion. That rectilinear motion is still under translational motion, just that it's in a straight line. The next type of motion is rotational motion. Rotational motion. Examples of, I forgot to give an example for translational motion. An example of translational motion is me walking from point A to point B, or a rigid object like a car going from a particular type of place to another place, like going from Canada to Alaska, which is, I don't know if that's possible, or a plane going from Africa to Europe. And whether it's in a straight line or a curved line doesn't matter, just as long as it goes from point A to point B, and it still arrives at its destination. Rotational motion is the movement of an object around its axis. It's an imaginary line that goes through the object. So an example of rotational motion is maybe the Earth revolving around the Sun and the Earth in its rotation. If you've ever seen maybe pictures of the Earth, you would see that line that crosses through it. That line is the line of axis, or it's an axis that the Earth goes through. And also, the blades of a rotating fan, you see that thing that makes the fans rotate? That line that passes through it is the axis. Next is random motion. Random motion. Random motion, like the name suggests, is a haphazard and scattered type of motion. It doesn't really have a specific destination. It doesn't go either in a straight line, in a curved path, or even go around its axis. It just goes, I think I can draw that on the board. It just goes from wherever it can to wherever it cannot, obviously. So an example of this kind of motion is the movement of gas particles, or Brownian motion. This is named after Robert Brown because of his discovery of why gas particles move this way, due to their freedom from forces, which we'll talk about in chemistry. Lastly is oscillatory motion. Oscillatory motion. Oscillatory motion is also known as vibratory motion, and it's a periodic motion that goes from point A to point B, back to point A, back to point B. An example is a simple pendulum. A simple pendulum, I'll just draw something quick. A simple pendulum has or let me not draw that there so you can see it clearly. I'll draw it here. All right, so this is the wall. Let's say this is the string, and this is the bob. So the bob goes from point A, let's say this is where it is, and goes to point B. If you've ever seen a pendulum before, which I suggest you have, and even if you haven't seen, you'll see videos of pendulums going from point A to point B, to point A to point B in a periodic motion. And now that we've talked about types of motion, I'm going to explain to you one special type of motion, relative motion. What is relative motion? Relative motion is simply the way an object perceives another object's motion. So an example is, if you're traveling and you look outside, you see trees, right? But it's as if the trees are moving. Have you ever noticed that? Like, you look outside, try to imagine that your car is stationary because you're in the car, right? If this road is smooth and the windows are shut, you wouldn't actually think you're moving. You would think you're just stationary. But if you look outside, you see that the trees are the ones moving, or the ground is the one moving. Why? That is because you are perceiving the movement of the object, which is the car, with a perspective of the earth. What I'm trying to say is that you are the trees are moving outside because you are moving at the same speed as the earth is moving, or sorry, as the car is moving. You are in the car. So because the car is moving at a certain speed, you're sitting in the car, you are also moving at that same speed because you are in the car are in the same position. But if someone were to look at you traveling, like just zoom off past the road, the person knows that the person is standing, but you're the one moving. And you like just arguably say like, why am I thinking that the trees and you are moving, like you are the one zooming past me and I'm not the one moving, and you are saying that the car is the one zooming past? Because these are two different people or two different objects seeing each other from different perspectives. That is relative motion. I advise that you also do some more research on relative motion and try some experiments of your own. And now I'm going to talk about distance, displacement, speed, and velocity. Before I talk about these terms, I want to tell you about scalar and vector quantities. Scalar and vector quantities. A scalar quantity is a quantity that only has a magnitude. Let me write that down. I'm going to explain it in a minute. Magnitude. And a vector is a term in physics that has a magnitude and a direction. Magnitude and direction. What do I mean? If I said, push this block, or let's say we have a concrete block, and you push this block, and I asked you, how far did you push it? You would just say, 5 meters. 5 meters where? That's where vectors come in. So when I asked you, how far did you push the block? You said 5 meters. That is a scalar quantity because you only gave me the magnitude, 5 meters. But to where did you push it? I pushed it from here to the right, or here to the left, or here forward, or here backward. So the direction you're giving is where vectors come in. So if you said, I pushed it 5 meters to the east, 5 meters due east, that is a vector. East. You see the difference between vectors and scalars? A scalar only has the magnitude, but a vector has both the magnitude and its direction, due east. That is where distance, displacement, speed, and velocity come in. Distance is how far an object has gone. So distance is a scalar because I only mentioned how far something has gone. But displacement is how far something has displaced from one position to another. It means displacement now has a direction. Displacement is like distance, but the vector version of distance. So I would say here the distance is, let me clean this off. It's 5 meters. So distance is a scalar, but displacement is a vector. And that is where speed and velocity come in. What is speed? Speed is how fast something is, right? How do you know how fast something is? You know the distance the person has covered divided by the time the person took. So if I asked you, okay, let me clean this off so I can write it down. Let's say you walked 6 meters in 2 seconds. How fast are you? What's your speed? Your speed is basically 6 divided by 2, which would give you 3, right? Now, speed is the scalar version with distance, while velocity is the vector version of displacement. So let me write down the formula for speed. From what I just said, speed, let me write that down. Speed is equal to the distance covered divided by its time, or the time taken. So this is what speed is. And velocity is the exact same thing, only velocity is not distance, velocity is displacement. So let me write it down as well. Velocity is equal to displacement. Sorry, it's supposed to be display, not display. Displacement divided by time. Alright, so velocity, like I said, is the vector version of speed, but we mostly use velocity when it comes to physics because we have to give direction. Before I jump into acceleration, I want to tell you something called a displacement time graph. We use graphs to be able to give us a clearer picture of how something moves, how an object moves. So let's say I have a graph, and remember, a graph in a Cartesian graph or a linear graph has an x and a y axis. Y axis, x axis. Oh, sorry, wait. A Cartesian plane has an x-axis, and the x-axis is horizontal, x-axis, and the y-axis is vertical, y-axis. So the y-axis is the displacement, and the x-axis is the time. So if the velocity is constant, you're going to get a constant slope, a not too steep slope and not too flat slope. You're going to get a straight slope if the velocity is constant. To know if an object is faster, the slope would be steeper. To know if an object is slower, the slope would be flatter. Let me explain what I mean. Let's say, okay, let me say an object. Let's say the time is from. Let me remove the t here. Let me say, this is 0 seconds, 2 seconds, 4 seconds, 6 seconds, 8 seconds, and then 10 seconds. And let's say the displacement is 50 meters, 100 meters, 150 meters, and let's say 200 meters. Okay? If an object goes from 0 meters, which is here, to 100 meters in just 2 seconds, you see where the slope is. You see the line here? I gave it's 100 meters in 2 seconds. This is the slope. And let's say it goes 150 meters in 4 seconds. So 150 meters in 4 seconds. You see the line? And let's say it gave 200 meters in 6 seconds. 200 meters in 6 seconds. You see how high the slope is? Now, let me give you a different scenario. Let's say that same object, for whatever reason, just started getting slower. And let's say it could only get 100 meters in 4 seconds. It could only get from 0 meters to 100 meters in 4 seconds. This is how flat the slope would be. Let's say it went from 150 meters in 8 seconds. This is how flat the slope would be. And let's say it went 200 meters in, let's say, 12 seconds, or let's say 10 seconds. So 200 meters in 10 seconds. So as you can see, as I drew this line here, it was very slow, but at this point, 8 seconds, it started getting faster. It went from 150 meters to 200 meters in just 2 seconds, because the difference between 8 and 10 is 2. But as you can see here, it was very slow, and then it started getting faster. So what I'm saying is a displacement time graph tells you how fast or slow an object is, because it's telling you if the velocity of the object is constantly changing. And now that I've explained this, let's dive into acceleration. Acceleration is the rate of change of velocity. It means how fast velocity changes with time. So the formula for acceleration is velocity divided by time. All right, great. Now, this acceleration is a vector quantity because we're talking about velocity, which is a vector quantity of displacement. So acceleration is a vector quantity. And I also forgot to tell you about its units. Remember when we were talking about units and measurement? I told you I was going to explain acceleration. I was going to tell you about its units. So let me go back to velocity and tell you about its units. Velocity. Velocity is distance divided by time, right? Okay. Divided by time. If you remember from our units and measurement video, distance is measured in length, which is meters. So it's not supposed to be L, it's supposed to be M. Distance is measured in meters, which is M, and time is measured in seconds, which is S. So velocity is measured in meters per second. You can either write it like this, or you can write it like this. you're basically dividing meters by second. This is basically meters per second. Now, what is the unit for acceleration? Since we know the velocity is meter per second, this is going to be equal to meter per second divided by time. Time is second. So remember when I said that meters divided second to give you s raised to the power of -1. If you divide it by another s, you're going to get ms raised to the power of -2. So let me clean this off so you can see the unit. So the unit for acceleration is equal to ms raised to the power of -2. And before I go, I'd like to tell you about velocity and time graph. This is the last part of this lesson. So velocity and time graph, just like displacement and time graph, tells you how fast or slow acceleration is changing. The opposite of acceleration is deceleration. Deceleration. Okay, and just like I told you that the displacement time graph tells you how fast or slow the velocity is, the velocity time graph tells you whether an object is accelerating or decelerating. So the velocity time graph is entirely different from a displacement time graph. The velocity time graph would look something like this. Okay, so you know this is the x-axis, and this is the y-axis. Sorry, I wrote that like a 4. It would be something like this. So let's say this is velocity, and this is time. This is how it must always be. Time is the x-axis, and velocity is the y-axis. If an object is constantly accelerating at a constant, that means it's constant, it's uniform. It means that for every second, the velocity is increasing constantly. So let's say the velocity is 2 meters per second. It must be increasing 2 meters every second, 2 meters every second, or 2 meters per second every second, 2 meters per second every second. So if it's constant, right, like I said about the displacement time graph, if it's constantly 2 meters per second, 2 meters per second, you're going to be getting, sorry, I wrote that here. If an object is constantly moving 2 meters every second, 2 meters every second in the displacement time graph, you're going to get a constant slope. But when you want to find the acceleration and you're using velocity time graphs, you're talking about how many 2 meters per second is in 1 second. So if you want to find out the acceleration, constant acceleration of an object, it's going to be increasing 2 meters per second every second, 2 meters per second every second. So it's going to be accelerating every 2 meters per second. So that's what it's going to be doing at this point. And then let's say for some reason the object just keeps moving at a constant velocity. It doesn't keep increasing at 2 meters per second. It just stays at 0 meters per second. It's going to have something like this. And let's just say for some reason the object now decreases its speed. The object is now going to decelerate. This is a typical example of this is maybe if you're driving from home to school. If you're driving from home, you have to, when you get into your car and you're on the main street, you're going to be going at a constant speed and be accelerating constantly. And then at some point, you've gotten to your maximum acceleration. You now just move at a constant velocity. You're not decreasing your acceleration. You're not even increasing your acceleration. You're just constantly moving at a constant velocity. And then when you're nearing your school, you have to definitely hit the brakes. And that's when you start to decelerate at this point and arrive here. That is it for velocity time graphs. Now it's time for the questions. Number 1, give me another example of relative motion. And number 2, give me another example of an object moving with a velocity time graph. If you enjoyed this lesson, please like, subscribe, and share with at least 3 people you know don't have access to basic education or who is bold enough to explore homeschool. And I'll see you in the next class.